A cat is placed in a sealed box along with a radioactive source. At some point in time, a nucleus of the substance may decay, releasing a lethal dose of radiation that kills the cat. But until this event has been observed or measured, the cat can be said to be simultaneously dead and alive. A would-be observer outside the box can't determine the state of the cat. This thought experiment may initially seem absurd, but the cat paradox, devised in 1935 by the physicist Erwin Schrödinger, is a popular image illustrating the nature of quantum physics. This branch of physics is concerned with the characteristics of microscopic systems, the structure of matter, and its interaction with light. Quantum physics says that electromagnetic waves, such as light, are also particles, and that particles simultaneously have properties of waves. This notion sounds incredible, but it's true. It can be proven in a famous experiment, the double-slit experiment. Electrons are fired at a wall containing two slits, through which electrons can pass. Behind the first wall is a screen that detects each arriving electron. What pattern will the electrons produce on the detector screen? If electrons were only particles, one would expect to see two stripes consisting of many small points, each representing an electron passing through the one or the other slit. But that isn't the result. Instead, we see a pattern of several thick stripes at a certain distance from each other. This is identical to the interference pattern produced by waves passing through the slits. The inevitable conclusion of this result, bizarre as it may seem, is that an electron is both a particle and a wave. This is a manifestation of what's called the duality of quantum mechanical objects, and their state depends on their measurement and the observer. This notion was a revolution in physics. In classical physics, there were assumed to be laws describing the exact and objectively measurable behavior of objects at all times. Quantum physics cast doubt on this worldview. The originator of quantum physics was Max Planck. In 1900, he formulated a law that, for the first time, explained what was known as black body radiation. The principle behind it is that the electromagnetic radiation emitted by such a body does not vary continuously, but in concrete jumps. These energy packets, the quanta, are dependent on the frequency of the radiation. Planck identified a constant relating the energy to the frequency, known as the quantum of action. In 1918, Planck received the Nobel Prize for this discovery.
Es ist Ihnen schwer zu verstehen, wie, als man die Gesetze des photoelektrischen Effektes noch nicht kannte und noch nichts vom Compton-Effekt wusste, wie schwierig es war, in der schwarzen Strahlung diese Quanten zu finden, wo sie viel versteckter vorhanden sind, und welche Großtat es war von Planck, eben in dieser schwarzen Strahlung diese Quanten zu finden. Es war, wie er selbst sagt in seinen Erinnerungen, ein verschlungener Weg.
He wasn't particularly happy about his own idea. The new insights seemed too unsettling. They didn't fit into the worldview of the time. But Albert Einstein took up Planck's idea and postulated in 1905 that light also consisted of discrete energy quanta, which he named photons. With this, he explained why, when a metallic plate is irradiated with light, it could eject electrons. The number of emitted electrons is proportional to the intensity of the irradiated light, a phenomenon known as the photoelectric effect. Einstein reportedly said about his discovery, "This is the only truly revolutionary thing I've ever done." Although when most people hear his name, they think of his theory of relativity. Planck was skeptical about the hypothesis of the photoelectric effect, but Einstein stuck to his theory and was awarded the Nobel Prize for it in 1921. The new ideas of Planck and Einstein galvanized the research community in the early 20th century, and also provided major inspiration to physicists.
It was the first international meeting of that kind where physicists got together to discuss fundamental problems in their field. And these conferences played a very unique role in the development of 20th century physics, most notably in the area of the quantum revolution, whose birth indeed overlapped the initiation of these meetings. This is the famous photo from that first conference, which you probably have all seen. It's a quite illustrious group of 20th century physicists, including 8 Nobel Prize winners who had won the Nobel Prize or would win the Nobel Prize in the next few years among the 24 physicists gathered in this room. Here you see many of them, whose faces you recognize, and much attention has been paid to this picture of Einstein here, which shows the young Einstein. He was 32 years old, and people have tried to explain what he was symbolizing with this signal. Some people have interpreted it as a Buddhist message. I actually think he's holding a little cigarillo.
New discoveries rapidly followed in the young field of quantum physics. Niels Bohr applied the quantum hypothesis to Ernest Rutherford's atomic model and refined it. Bohr's model views an atom as consisting of a nucleus and electrons that circle the nucleus on certain orbits associated with certain energy. The electrons can jump from one orbit or energy level to another by absorbing or emitting energy of a corresponding frequency. What consequences that has, why the observer determines whether Schrödinger's cat is dead or alive, and how quantum physics pervades daily life is the subject of Part 2.